some point. Yes.
Good morning. Good morning, everyone. It's our second day for our MAM 12 conference. We are going to start our second day by our keynote speaker, Professor Amy Ward from Booth School of Business. She is the previous MSOM Fellow and also an Editor-in-Chief in Operations Research. I was the session chair for this session, but I was not aware of it. So that's why I have not prepared. I should have been, but that's why I have not prepared a full introduction. Yeah. So that's why I have not prepared the proper introduction. So that's why I'm just going with these two highlights. And with that, I'm going to leave the floor to Dr. Ward.
Thank you very much. Can you hear me okay? And I prefer short introductions, so that's perfect. Let me start by saying I really thank you to the organizers. I'm really enjoying being here. It's a fantastic conference. Fields Institute holds a special place in my heart because my first publication was in a Fields Institute communications. So it's special to me to be here. Today, I want to talk about integrating machine learning and queuing to enhance decision-making and application to criminal justice. Acknowledge my academic collaborators, Pengyi Shi and Jichang Zheng. He's a third-year PhD student, or just finished his third year, entering his fourth year. We have a community partner that is Adult Redeploy Illinois. I'll say a bit more about them in the case study at the end. And I should thank the Russ Sandy Center for Social Sector Innovation at Chicago Booth that got us aligned with our community partner. Let me start with the motivation for this work. Overcrowding is a major concern in the US justice system. Individuals suffering from substance use disorder are a major contributor to overcrowding. So drug offenses are a very common reason for arrest in the US. The purpose of incarceration is not to solve addiction issues. So the result can be a vicious cycle, or this revolving door between crime and recidivism. So what got me interested in this project was I heard this number and it said it could be 70% recidivism in the US within 5 years. So recidivism is I get out of incarceration, I commit a crime, and I go back. So the recidivism is the act of committing another crime. And that seemed really high. So I was like, wow, what are we doing about this? There are incarceration diversion programs in the US. So this is a program that would be focused on rehabilitation, not incarceration, a focus on rehabilitation. And if I look at recidivism reduction numbers for going through some of these rehabilitation programs or these incarceration diversion programs, I get something like 30% for substance abuse treatment programs, 8% and 32% for cognitive behavioral programs, 20% for education and employment programs. So this is the reduction in recidivism after successfully completing the program. This is not my bread and butter research, so I trust these numbers. I take them at face value. I'm not trying to do a program evaluation and tell you about how successful or not successful these programs are. I'm ultimately an operations person, and I'm interested in capacity. And so my problem is there's not enough capacity for everybody. So my research issue then is who to admit. And I want to admit the people that I can help the most, that I have the best likelihood of reducing recidivism in the long term, because I'd like society to kind of be in a better place. So my goal in my research issue really is this: who to admit. Let me zoom out a little bit and just think about the overall process flow. I'm sweeping a lot of details under the rug, but I just want to have a sense of, in the space of the US justice system, where would an incarceration diversion program sit? So you have an arrest event, and then you're guilty or not guilty after you go to court. Then there's a question of, are you diversion program eligible? So yes or no, so there's some standards. The diversion program, maybe in conjunction with the judge, is going to decide, are we admitting you to the diversion program? Now, I guess an individual has a choice. They could say no, but generally, at least the diversion program we're working with, if you don't go into the diversion program, you're being incarcerated and you're behind bars. So this is kind of a choice most people want to accept. If I put you in the diversion program, you are not physically behind bars. So there is some risk that you're going to commit a crime. But what I'm hoping is you're going to successfully complete the program, you will be better integrated into society, and there's lower risk that in the future period, you'll commit a crime. So these are kind of the risks I'm balancing when I'm thinking about who are the best people to admit. If I don't admit you, then I'm sending you to jail or prison, and after you get out, there's this higher recidivism risk. I'm focusing right here. So I'm focusing on a stream of people that are coming in, that they're diversion program eligible. So I've decided they meet the criteria. I still don't have enough capacity to accept all of them. So I'm trying to think about, of the stream that I'm seeing, which are the ones that I'm best suited to help. Okay, and so we hope that these programs are going to help us from a societal perspective in terms of long-term benefit. When I say ARI eligible, there's something called an LSIR risk level. So this is something about the riskiness to commit another crime. This is a nationwide score. ARI, Adult Redeploy Illinois, this is the incarceration diversion program we've talked to, has a philosophical idea that they'd like to focus on kind of harder cases. So if you're a 16-year-old and this is the first drug offense and you come from a pretty high status socioeconomic class and a stable family, this is probably not the target audience. You should be thinking about a target audience that's maybe a little bit more disadvantaged, more socioeconomically disadvantaged. So ARI eligible, I'm sort of looking at riskier cases. I'm a queuing theorist. If I think about the queuing admission control problem here, we're going to see people coming in. They've committed an offense, and I see their covariates. So I see your age, your sex, how many crimes you've committed in the past, whether or not you're employed, whether or not you have stable housing, what's your financial status. You can think of all different things here. Then I get to do a classification based on the X, and that classification is going to help me decide whether or not I want to admit you. So you go into the diversion program, either you recidivate or you renege. I'm probably going to use these terms interchangeably. Luckily, they both start with R, so they're kind of similar. From the queuing theorist point of view, I'm thinking of this as a renege event because you're leaving before you finished your service. This corresponds to recidivism in my application. And so either you're recidivating or you're successfully completing the program. And there are some people that there's a very few number that the program sort of lose track of. It could be a good thing. It could be that you haven't met your case officer for a couple of weeks because you are now full-time employed and you were at your job not meeting your case officer. But that's a pretty small number. So for the purposes of my model, I'm going to say either you're recidivating out of the program or you're successful. Okay, so I'm thinking of this as a queuing admission control problem in a finite capacity model because I only have a certain number of slots for people in the diversion program. That really depends on the number of case officers I have. So it depends on how many people we want to put a case officer can handle. And there's a noisy classification because I don't really know when I see you, I don't know, are you a real high-risk person to commit another crime? Or are you a low risk? I'm making some kind of prediction about that. It's a noisy classification. A little bit about the partner data that we have, just so you can see where the program is operating. So the program operates in Illinois. I have color-coded all the counties that it operates in. We're looking at data from Cook and DuPage. Cook is the largest county in Illinois. DuPage is where the program's been running the longest. So you can have a sense. We don't have a ton of data. So one thing to keep in your mind in this age where everybody talks about tons of data, this is what, like 125 individuals a year, something like this. And we've got data for about 10 years. So it's even a little less than 10 years. So it's not a ton of data. That's the one thing to keep in your mind. The other thing to keep in your mind is a lot of times when I think of queuing models, and maybe this is my bias, and I think of service times, I'm thinking of like, maybe I measure service time in minutes, or maybe hours, probably not hours. This I'm measuring service times in years, because my service time is equating to the length of stay of somebody in the program. So when you're thinking of timescales for this model, you're thinking about a service time where somebody is in that program for sort of 1 to 1.5 years. If you look at percent that are recidivating out of the program, it's sort of in the 20-something% range. And as far as we can tell, looking at other nationwide incarceration diversion programs, that's the right order to be looking at. That's the right approximate percentage that you're going to get recidivating out of the program, assuming you do some kind of reasonable matching, reasonable admission. I'm looking at the length of stay in DuPage and Cook. I don't see that there's a huge difference there. The length of stay I'm plotting, this is unconditioned. So this is combining together people that have reneged and people that have successfully completed the program. The thing I want you to observe is that we tried to fit a lot of common distributions to this, and we did it on the conditioned times too. So conditioned on you recidivating or conditioned on you completing the program. And there's not a clear named distribution. Okay, so it's not exponential. It's not exponential. If I showed you a discrete fitting, it's not Poisson. And I'm emphasizing that because that means for my queuing model, if I think about key modeling features, one modeling feature I want is I want a general service distribution. I don't want to assume exponential service distributions because it's really not fitting my data. That means if you think about it, I've got a more complicated problem because if you think about the queues where it's a general service time for everybody in service, I'm needing to track how long they've been in service. So it's going to give me a complex state space. The other modeling feature I'll mention is this is a reneging during service. So if I let you into the program, I don't really want a long delay before you get in. I don't want you to be thinking about long wait times. It's the judge and ARI have agreed that you get into the program. This should not be a year later that you start the program. Okay, so think about it as pretty short wait times. And so when I say finite capacity, I'm being a little bit vague on this, which you'll understand in a minute. Think about, I let you into the program. I'm expecting that quite soon after I let you in, you're going to start. Okay, so I'm thinking of something where there's not really any buffer that you would renege from. It's just while you're in the program that I will see these reneges. So let me say a little bit connected to past literature. So admission control and queuing, that's ultimately what we're solving. This is a very long-standing problem, lots of research on it, but there's not that much research where you have unknown classes. And so, inspired by, I'm also inspired like Doug, which is, there are a lot of models where I have to do this prediction before I know what to do with somebody. And I agree with you. That's a really interesting question. And that's kind of the part that I really want to focus on is I'm trying to do some kind of admission control, but I got to do some kind of noisy classification first. It's a decision with imperfect information, which is what I just said. There's a really nice paper by Argan and Zia that we were inspired by. They have a priority model, priority scheme for, this is actually scheduling. This is a who to serve, not an admission control. But there's a similarity because we're also going to have some kind of priority rule. We're going to have some less restrictive assumptions on our signal, some less restrictive signal assumptions than they do. We're not the first paper to do queuing in criminal justice. I would say compared to some of what we've seen in the literature, we're placing a little bit more focus on developing an analytic model rather than simulation results. There's quite a bit studied on multi-class GGN plus GQs. That's something that I've been very interested in. A lot of the work has the reneging during the waiting, not in the service. And so the reason I emphasize that for this application, it's important that there's not really much waiting and the reneging is during service is because in comparison to some of the theoretic results in the literature, I can't really leverage those. We're not the first to think about reneging during service, but the other papers we found have either exponential service or exponential reneging. I'm going to have general service and general reneging. All right, so I guess I'm about 15 minutes into the talk. Let me give you the outline. You've got the problem. I want to tell you what is my exact model formulation. I haven't quite done that yet. Then I want to tell you what's my proposed admission control policy. Then I want to do a little bit of a case study. So let's think about admission control with unobserved classes. And I'm going to try to separate with my colors. Black is known. Blue is what is unknown, and my vectors are in bold. So we have this arrival rate. Somebody's committed an offense. I see this covariate vector. That's like your age, your sex, your crime history, these types of things. And I'm going to classify you as, think high risk, low risk. I could do high risk, medium risk, low risk, but I think for the purposes of thinking about it, you can think of the J being 2, and I'm classifying you into high risk or low risk. I don't know for sure what that classification is. So this is a latent feature that I don't get to observe. I make the admission decision. And when I make the admission decision, if I decide not to admit you, there's some kind of denial cost. And you can think about the denial cost as the financial cost of incarceration, plus potentially any future costs because you're sort of not getting the benefit of this recidivism reduction if you successfully complete the program. So the financial cost is going to be pretty obvious to calibrate. The other cost is a little bit fuzzier to get your hands on, but you could include it in there. There's a true classification. So I'm going to assume there's an underlying P. That's my true classification. And that tells me for a given covariate X, are you high risk or low risk? That's what I'm trying to estimate. So I'm going to do an estimated classification. And that's my P hat. I only get to see P hat, not P. And now if you go into the diversion program, so there's some probability you renege or recidivate. There's some probability you successfully complete. If you renege, there's some kind of cost associated with that because you've committed another crime. There's another trial. The crime costs society. That's what the CJR is. If you're in the program, there's a holding cost. And so the holding cost is I do have case officers. I have to monitor you. And so that's my CJH. And if you want to think about these numbers, CJH is maybe like 5,000. CJH is like maybe 50,000. Okay, so there's probably an order of magnitude difference between the CJD and the CJH. It is this probability of reneging and this reneging cost that would really be driving up the cost of letting you into the program. Okay. In the program, there's expected length of stay, so that might be class dependent. The 1 over tau j is the unconditioned expected length of stay. So the high risk class that has higher chance of recidivating, I would expect that to be a little bit lower because if you recidivate out of the program, that's cutting your time in the program short. There's some kind of censoring there. I can see the population of covariates at any time t. So for a particular covariate, the ones that are males and 30 and have committed one crime in the past. I know exactly how many there are. What I don't know is the class population. And if you notice, it's the class population that is driving, for example, whether or not you renege or whether or not you don't renege. So if I look at my data, I see my arrivals, I see what their covariates are, and I see whether or not they reneged from the program. Okay? That's what you should think of as my data. Yeah.
How big is kept from track? How big should we think the number of classes?
2. Yeah, and when I do my case study, it's going to be 2. The more classes I put in there,
Basically small.
Small. And the reason you might think about, why am I introducing these classes at all? Because I could think about classifying directly based on the covariate. And the reason I'm not doing that is because I have this limited data. So it is, if given the limited data, it is easier for me to calibrate the model if I kind of bring in these classes and it's a small number of classes, and then I'm kind of reducing the amount of stuff. It makes the calibration of the data easier.
If someone has gone through the program and then they come back, are they eligible to go through?
No.
The program? No.
Yeah,
One
once.
time.
One time thing. And you notice I'm not actually modeling out into the future. Like if they've successfully completed the program, that would be you can imagine like a model that's capturing the long-term benefit a little bit better. And I think that's really interesting. And that's something that we're thinking about. But this particular model, I'm only capturing it through how you might calibrate that CJD. And the goal then is I want to minimize long-range average cost by deciding who to admit. The costs I'm trading off are this denied cost of admitting with this reneging and holding cost if I let you in. And in answer to Peter's question, the J would be much less than the number of covariate combinations, and that makes the model more amenable to calibration when data is limited. So you should think about some kind of mixture model in the background, and when you think about a calibration, you should think of some kind of EM expectation maximization type algorithm. Oh, and then I had this little diagram. So I see the X, there's latent classes that I don't see, and the latent classes that I don't see are determining the R, which is 0 or 1. Did you renege from the program or not?
The QJ, I don't think is not, because you don't know if I'm a class J or I'm not a class J, right?
Oh, if I don't know if you're a class J or not, but if you tell me that you're a class J, then I know it is 80% probability, for example, that you renege. So you tell me you're a high class?
That's the assumption that you're making.
Yes. Yeah, so for example, I would know there's high class and low class. I know for the high class, it's 80% probability that you're going to recidivate, but when offer shows up, I don't know if I should classify you as high or low. Correct. Oh, I guess it doesn't depend on the X in the sense that conditional on me knowing J, conditional on me knowing what class you are, then it's QJ. But if we start with the X, then it's going to be like a multinomial coin flip to decide what class you are. So I could have a QX and QJ would be related by QX through the probabilities of which class you are given I know your X.
So you need to some CJR. I understand you have it. You know, I know if you're at that level, you're a high customer. I know what you're customer, but UJ, you need to estimate from data to some extent, and you have an issue with this estimation. So thank you.
Yeah, I'll say a little bit about that more later, but you've hit on exactly one thing, which is when I calibrate it from data, I have to kind of look at the data and guess that like, okay, it's a little bit bimodal. These kind of people look like I'm going to do high class. These kind of people look like I'm kind of going to do low class. And I'm making some judgment calls there as like, I'm going to use 2 classes, not 3 classes. And we tried when we looked at the data, should we use 2 classes? Should we use 3 classes? And there's, so there's a little bit of not perfection, I'll call. Yeah, but I think you could think about when I go into the model, like you can look at other studies, and there's a lot of other studies that are saying there's high class and low class. high class, kind of think about like high class, 80% probability to renege, low class, like 20% probability to renege. You could almost think about setting that ahead of time. And then from your data set, you're going to take the X's and decide, given the X's, what's the probability that I put you in this high class or low class? So you could almost think about those classes as being preordained, predefined. So just to say again, something about the state space. So if I want something Markovian, I've got time elapsed since the last customer arrival. I've got this vector of measure valued processes tracking the ages and service of each covariate. And what I don't see is this vector of measure valued processes tracking the ages of service in each class. This is not observable. So I really have some partially observable state space here. So that's really hard to solve exactly. I'm not going to try to solve it exactly. My approach is going to be to lower our aspirations and solve a static admission control problem. What I mean by static admission control problem is I'm not going to see Mark come in and decide whether or not I admit you, and then Ofer come in and decide whether or not I'm going to admit you, and then Barbara come in and decide whether or not, Margajada come in and decide whether or not to admit you, and do this one by one. I'm going to think, I know Ofer's covariate class. I'm going to decide whether or not to admit his covariate class. I know Mark's covariate class. I'm going to decide whether or not to admit Mark's covariate class. And I'm going to solve that up front. So I'm just going to solve for each of these covariate classes, do I admit you or do I not? The dynamic execution of that is something I will leave for second stage optimization. As long as you use a dynamic execution policy that matches in the long term what I tell you what to do with the classes, we're good. If that didn't make sense, I'm formulating the problem in a second, and it may make sense on the next slide. I think I got ahead of myself a little bit in explaining. The audience challenge is I'm not actually using matrix-analytic methods to solve this. So the audience challenge is I think there's another way to go about it, and I challenge you to tell me how to do that. Okay, so when I say static admission control problem, I am ignoring the discrete and stochastic nature of the arrivals. So I have a true problem and I have an estimated problem. The true problem assumes I know the P. If I know the P, my arrival rate is just lambda times the expected probability U in a class given the X, the covariate I see. So X is the covariate random variable, PJ is the probability U in a particular class given I saw this covariance. So then my decision variables are going to be an A of X, which is the fraction of covariate X to admit. So I see you're female and you're 20 years old and you've committed 3 crimes in your past. I'm going to say females in that bucket, we admit all of them, for example. I could also say I admit 50% of them. The class JQ, then I can do a Little's law. This bit on top is the rate of admission of that class, and 1 over tau j is the time. So my feasible region then is the A should be between 0 and 1. And if I add up the number of people from each class, that has to be less than or equal to the capacity that I have. If I look at the estimated problem, I'm estimating the arrival rate. So basically everywhere you see P, I'm going to replace it by P hat. So I'm estimating the arrival rate. I'm making the same decisions. I then have to estimate what the class JQ length is. And I have a feasible region. And the reason I put a hat here is my feasible region does depend on what my estimated Q lengths are. And there's a little bit of error here, okay? I haven't given you my objective function, so let's just write out the objective function. So for the true problem, I have a cost of denying admittance. So it's CJD, that's the denial cost. That's like my financial cost of incarceration plus any other long-term costs. And then these are the rate at which I'm denying people at entrance, given this particular control policy. Then I have a cost to hold people in the program. And then I have a cost from recidivating. I'm summing over all the different classes, and that gives me, the objective function of the true admission control problem. The estimated problem, it's exactly the same, but I've replaced the blue P with the P hat. I'm going to define what I'll call the treatment cost. So the treatment cost is basically your holding cost plus your reneging cost. If I do that, I can rewrite the objective, and you can see that the objective function is basically for each class balancing a denial cost with a treatment cost. Okay, same thing here. And so let's just summarize what's my estimated and my true control problem. Estimated, I've got hats. So I'll think about the decision variables with the hat, and I will put a star to tell you what is the solution. Okay, so I'm going to be interested in the difference between the solution of the A hat star, the solution to the estimated problem, and the A star, the solution to the true problem. Okay? And one would imagine that the better P hat estimates P, the closer those two solutions are. But that's basically what I want to get at. Okay? An excellent question, which is about what I was going to do. So if you think about this feasible region here, because Q hat is estimated, if I set N hat equal to N, these two feasible regions may not be the same. And so that means I may be overusing the capacity I have or underusing it. If I want to compare these two solutions and do something kind of reasonable, I think the most reasonable thing to do is to choose the N hat to make sure that the capacity I use is exactly the same. So given the estimation, I'm going to choose N hat to make sure that I'm using exactly N capacity. Now, my fudge here is, wait, but do I see that? Well, I'm thinking if I'm doing this, if I'm executing this policy, I do see who is in the program, and I get to make a decision. If I have additional capacity, I get to bring somebody else into the program. So I'm thinking that I would use all my capacity. If I wouldn't use all my capacity, it's not really an interesting problem because I let everybody in. So that's, I'm fudging that a little bit, but that's how we're going to compare the solutions.
Your policy does not depend on how many people are already in the program, how big is the program?
No. So when I said I'm lowering my aspirations to the static admission control problem, you got exactly the main thing that I was doing in lowering my aspirations is I'm making decisions that are not state dependent. And so I am fully just saying, these are the covariates. These are the covariates I want to admit. These are the covariates I don't want to admit. I'm ignoring capacity in the program. If you think about, and I think this is actually a really interesting future research question. If you think about how I would actually, given an A star, how would I actually implement it? I am going to be looking at what the capacity is. I'm going to be saying, oh, I've got some additional capacity. Now, I wasn't going to admit you, but maybe you still look kind of good to admit. I've got the additional capacity, so I'll admit you. But then I have to worry if I admit you, maybe later in the future, somebody's going to come that would be better to admit more. I'm not specifying how you would make those trade-off decisions. We can think about a lot of different ways to do it. I'm assuming that you will make them in such a way that on the long run average admission that you do for each class will get you to A hat star. And you can imagine different types of policies that would get you there. Yeah, good question. Okay, and I think I just said this to Doug. So capacity is not sufficient or else you don't have an issue. So one of the reasons I wanted to think about this true admission control problem solution is you look at this is a linear program. You probably have some idea in your head that, oh, this maybe looks a little bit like some kind of prioritization type policy. You are exactly correct. So an optimal policy prioritize admitting those with higher scores. And my scores are going to be based on, this is the difference in the denial costs and the treatment costs. For a second, let's just pretend the denominator is 1. So that says that I would be ordering you by, I want to give highest priority to people that have the biggest difference between the denial cost and the treatment cost. So if you observe, if I know, given your covariates, exactly what class you are, I have a solution that's a C-mu type rule. And the ranking depends on this difference between the denial cost and the treatment cost, modified by the length of stay. Right. So let's just visualize this. So what I'm doing is I'm sorting the classes into what I'll call X plus. These are the covariates with higher scores, and X minus. These are the covariates with lower scores. And I have a threshold. The threshold is a boundary covariate. What is the boundary covariate? Well, I'm going to determine the boundary covariate so that if I let everybody in the X plus set, I have not used up all of my capacity. If I let everybody in the X plus set plus the boundary covariate, then I go over capacity. I mean, I guess if you're really lucky, that would be exactly equal to N, but that's kind of a knife edge case. And so what's that telling you is I'm determining the set of covariates that I want to admit a particular set of covariates, a set of covariates that I want to deny, and there's one boundary covariate, and I will just partially admit that boundary covariate depending on whatever capacity I have left. Oh, and I should say we're assuming this is positive, because if it's not positive, I don't want to admit you. So let's think about a proposed admission control policy. So estimated static admission control problem solution. So it's the same thing, right? It's going to be a priority score policy. The only difference is the priority score policy is based on this S hat. So when I do the priority score policy and I do this estimation of my C difference in denial cost minus treatment cost moderated by the length of stay, that is based on a P hat. Okay? So I have a score function, but the score function is based on the P hat, not the P. So I'm not necessarily getting the same score. So you could maybe think of P hat as coming from a logistic regression. You could maybe think of P hat as a maximum likelihood estimation. I haven't right now specified how you got P hat. You did some estimations and you got P hat. So we're starting with you have P hat. So let's make an observation. I've said this as a proposition, but I almost feel like it's an observation. If I think about the S hat scores and I think about the boundary covariate, and I say your covariate and your score is higher than the score of the boundary covariate, and that implies that the true score of that covariate is also higher than the true score of the boundary covariate. What does that mean? That means in the true problem, we would be letting in the X covariate, and also in the estimated problem, I am letting in the X covariate. So that means that prioritizing according to S hat solves the true problem. So this is nice, but you're also sitting there thinking, why is that a proposition? I could have kind of guessed that. So really what we need is a sufficient condition for this to happen. Okay? So what's a sufficient condition for this to happen? Let's think about it first from the dimension of this X covariate space is 1. So think about the only thing I'm tracking is your crime history. If I'm tracking your crime history, you would imagine the more crime history, you've committed 10 crimes, you're probably more likely to commit another crime than if you've committed 1 crime. Okay, so that kind of suggests that maybe your condition should be something like a likelihood ratio condition. So my scores are increasing in the X, crime history, larger crime history, higher score. And I have some likelihood ratio order between the classes. So here GJ is the distribution of covariates X for class J. That would be a sufficient condition for this guy to hold. And I did it in 1 dimension because I think the intuition is a bit easier, but something very similar extends to multiple conditions. Let's do the intuition for this, because there's something nice about this. And what's going to be nice about this? So here's my crime history on the x-axis. On the y-axis, I have the p hat. The p hat is basically the probability you're from the higher risk class. So let's say I have 2 classes. P hat is just going to be the probability you're from the higher risk class. With 2 classes, higher score means I'm more likely to be thought of as class 1. So you could think about if I'm prioritizing according to the score, I'm also prioritizing according to the higher the probability that you are from the high risk class. Okay? And so if I use this threshold policy based on S hat, I could think about it as a threshold policy based on the P hat. The more likely you are to be from the high risk class, those are the ones I want to admit. The less likely you are to be from the higher risk class, those are the ones I'm not going to admit. Okay? Assuming I'm thinking that I want to admit riskier people. Okay, so let's say that I completely biffed. My P is way different than my P hat. Not looking close. But I got the trend right. So they are both monotonically increasing. This is great. This suggests that it doesn't matter how well I estimated P, as long as I got the trend right, my solution is going to be correct. Because basically both solutions are using all the capacity I have. In each case, I'm putting this threshold on the P or the P hat. They may not be the same threshold, but when I look at who I'm admitting, I'm basically admitting until I don't have any more capacity. And this is going to be exactly the same. These are the people I actually want to admit. These are the people that I do admit. These are the people in the ground truth I want to admit. That will coincide to the people I admit under the estimated problem. So as long as I get the trend right, I'm good. The problem is that's a pretty strong condition. Now, it may, I hope, I was trying to use an example that sounded sensible. It may sound sensible that if you've committed more crimes, you're more likely to commit another crime. But you know, I didn't tell you your age. So another thing that's true is the older you get, the less likely are you to commit crime. If you're 20 years old, you're more likely to commit another crime than if you're 50 years old. Now, how that interacts with your crime history, I don't know exactly, but it's also going to be true that as you're older, you've got more time to commit crimes. So it's not actually clear that this should be monotonic. It may be something like this. And if I get the trend wrong, now I'm not, this isn't working, right? Because here I've got some people that under the ground truth I did not admit, but under my policy I am admitting. Okay, so it's a strong condition, so I want to think about what can I say more generally. So let's think about, I'm going to first do this in the two-dimensional case. So J is 2. I'll say P hat is the maximum likelihood estimator. And I'm going to look at the difference between the scores. So I'm looking at the probability that the difference between my estimated score and my true score is greater than some small delta. And I have a finite sample bound on that. And you can see a few things that you would expect. So this upper bound is going to be smaller as the number of samples gets larger. That's what you expect. The more samples I have, I should be able to estimate that true score exactly. There is a smaller difference between the C mu rankings. So think about the extreme example. If my C mu rankings are exactly the same, then you're going to have an exponential to the something over 0. That's like exponential to negative infinity. You're going to have a 0 here. If my C mu rankings are exactly the same, who cares? It's all the same class. And also the other time is this reneging probability is closer to 0 or 1. So it turns out that this upper bound is going to be larger when the reneging probability is like a half. When the reneging probability is like a half, that's kind of a little bit of the harder case. It's a similar result when J is greater than 2, but it's not quite as explicit. So I put the J greater than 2 result. Now, of course, this is nice. Yeah?
Very confused about how you went on proving that. I mean, yeah, can you basically you observe something on the population, and it has a real correlation with your S of right, with your severity, I would call it, and you estimate it based on something. And you suggest that the estimation has a good enough correlation with the reality. Well, what's the step there?
I'm estimating the score function, and I'm basically using some kind of concentration inequality for, essentially what I'm doing is I'm flipping multinomial coins, right? Because the P hat is basically a flip of multinomial coins. And I'm using some kind of concentration inequality for the more samples I get, the more multinomial coin flips I'll get. And that's where I'm getting that like exponential decrease in the number of samples. And then the other stuff is just a few little things around the edges, but that's the core intuition.
Thanks.
So this tells me that the more samples I get, the closer I can get from S hat to S. That does not tell me the solution to my control problem. So how do I take S hat from S being close to A hat star being close to A star, right? So that's the other thing I want. If my S hat is close to S, I want to know about the A hat being close to A star. So let's think about this. I have these people I want to admit and these people I want to deny. I've basically separated out into an X hat region and an X hat or an X hat plus region. These are the people I want to admit based on the estimated score. These are the people I'm denying based on the estimated score. I have a boundary covariate that I partially admit. And let's see, I can use the S hat score to construct 1 minus epsilon confidence intervals around any particular covariate. So here's a covariate that comes in. The score is, say, in the middle of this confidence interval. So X has a high score. I can, based on the result you just saw, I can put a confidence interval around that score. I can do the same thing for the boundary covariate. This is a little bit trickier because the boundary covariate, which is the boundary covariate, depends not just on X, it depends on all the stuff in X hat plus. So this one's a little bit trickier. We can talk a little bit offline if you want, but I can also put a confidence interval around that. And I can observe that they don't intersect, right? So this is a case where I definitely want to admit. On the other hand, if I get somebody with a very low score, that's a case where with some confidence I can say I want to deny. So I can quantify this. This isn't a particularly good bound because that X might be large and okay, so it's not a particularly good bound, but it's something. But what happens when my confidence intervals overlap? I have either somebody where I look at the X, I construct their score, and it's overlapping with this boundary covariate. It's small, but it's kind of close to the boundary covariate. Or maybe I just don't have very many samples and I have a really wide confidence interval. Now what do I do? One idea is I could gather more samples. But let's think about this. This is a kind of high stakes decision making. It's a little bit hard for me to say, you know, I need a few more samples. So Mark, you have a really low score. I'm almost positive that if I put you in this program, you're going to go out and commit another crime. So pretty high risk to society, but I need some samples, so I'm going to let you in. So that's probably not something that wishes. So I have limited ability to explore here. And the other thing you can think about is human in the loop. And so one of the things I want you to think about is I have so much capacity for human reviewers, and we want to think about how humans can interact with algorithmic decision making. And so one of the themes here is, if I want humans to interact with algorithmic decision making, and I want to think about where do I best invest human capacity, we're going to suggest that the ones to best invest human capacity are the ones that are kind of around this boundary covariate. We're probably doing pretty okay with the machine learning algorithm for guys that have really high scores and guys that have really low scores. The intuition is that maybe we want the humans to interact and put their most effort into these types of scores. For ARI, it's not unreasonable to think about the humans interacting with the algorithm because we see that sometimes they do override in their eligibility data. I don't know exactly how they do this, so like I'm not going to be able to field questions on it, but we did notice that there are some people that are sort of not eligible that somebody must have looked at and decide, yeah, actually we want them to be eligible, so they would move them to a higher score to make sure that they're eligible for the program. Okay, so then I want to end a little bit with a case study. I want to think a little bit about, okay, so we have this idea that there's priority admission. I don't know exactly what ARI is doing, so I just want to claim that I'm not trying to, I'm trying to think about here at an abstract level, I am making admission decisions based on priority score policies. That is something in general we see done in practice. So I think the interesting research question here from an abstract level that you should be taking away is I'm doing priority score policies where I have noisy classification and we're trying to understand how good can you do or how well can you be off. Okay. And so now we're going to try to think a little bit with data, how do our results interact? Framework with policy evaluation. So I have a ground truth model calibration. I, of course, don't know the ground truth. But what I see is I have 646 data samples. Each data sample gives me everybody in the ARI program. I have the covariates of that person, and I have whether or not that person successfully completed the program. So the RI is a 0 or 1. The XI is these covariates. I'll tell you exactly what they are in a minute. So I'm going to pretend I have access to the ground truth. I'm going to calibrate a ground truth from that. And then I'm going to use that ground truth to generate semi-synthetic data, the exact same number of samples. And I'm going to construct a p-hat. Now I'm going to evaluate my priority policy because I have an s-hat and I have the ground truth. And I can see if I admit people according to s-hat, what does that look like when I know the ground truth? And that's how I'm going to do my policy evaluation. And I have this note, pretend smaller capacity, because the only data I have is from people that go through the ARI program. If you didn't go through the program, I don't get data on you. So for me to kind of do this, I need to pretend I have less capacity than I actually had. Okay, and I'm also going to need length of stay parameters and cost parameters. So let me talk a little bit about the ground truth model calibration. So from the data, the covariates we're going to look at are gender, race, the LSIR score, the employment, and the housing. And we did a bunch of different prediction algorithms, and those turned out to be the most important features. We actually have more features than that, but those turned out to be sort of the most important features in predicting whether or not you successfully complete the program. And we don't have enough data to, we have to be a little careful about how many features we include. J is low or high risk. The Q is basically 20% or 80%. And the data sample is, okay, so the X or the R, so I get a sample, I see somebody that is female, white, LSIR score 45, employment, full-time employment, unstable housing, for example. Sample size in is 646. I do the ground truth P from a maximum likelihood estimation. Okay, so that's going to be my ground truth P. And if you want to look at some of this interpretation, the housing risk and unstable employment, these tend to have the most effects, the most effect on how you're classifying the person, if you're classifying the person as high or low risk. And I could also do a plot that says which way. So just as a validation, if you have unstable housing, this is a feature value. Let's say you're high on the unstable housing. This means I am not likely to classify you as low risk. I'm more likely to classify you as high risk. And the way I did this, class 1 was the low risk and class 2 was the high risk. Length of stay parameter. So the class 2 is a little bit lower than the class 1. I, of course, don't exactly have this in the data. I mean, I don't know which class you are in the data. So I had to say, kind of do a little bit of look at the data. Here's going to be my class 1s. Here's going to be my class 2s. This is these guys are clustered because yeah, let me talk about that offline if you want. Cost parameters, there's a denial cost and a treatment cost. The denial cost then is the long-term incarceration cost. So that's something like $50,000 plus maybe you want to add a long-term cost. The holding cost is the program financial cost plus a rearrest cost. So the rearrest cost is depending on your QJ, and we'll use this financial incarceration cost. The reneging cost is basically the resentence cost. So that ends up being like $65,000. This treatment cost, so there's the holding cost in the program, that's pretty low, that's about 4,000, and then plus the probability that you get rearrested times this cost, and these turn out to be something like this. So I'm showing you this because this is basically class 1 has the lower cost the way we've calibrated it. Class 2 has the higher cost. Class 1 is my less risky class. Class 1 is my 20% probability to recidivate. Class 2 is my 80% probability to recidivate. So I am basically proposing in this ground truth, the ground truth policy is I want to admit people that are lower risk. Now, that really depends on how you do the cost calibration. When we did the cost calibration, I put this in parentheses because we didn't calibrate a long-term cost because I said it was a little bit fuzzier. If you add a long-term cost here, then that's going to switch your priorities so that you would prioritize the higher risk class over the lower risk class. I'm not claiming how ARI is doing this. I'm just observing that in our model, those are the factors that are influencing which one you put as your higher priority class to admit. Okay, so that just said cost groups. Cost calibration motivizes prioritizing the lower risk individuals. Lower risk is what we're doing. If I added the long-term cost, I'd be prioritizing higher risk. Okay, so now let's look at this evaluation. So I want to compare how I do with S hat versus what would happen if I used S. So I'm generating 646 samples from this simulation oracle. I'm estimating P hat. I'm using the MLE to estimate P hat. And okay, so you've got your priority score on the x-axis. I've got the covariate index on the y-axis. It doesn't really mean anything because I've just numbered them. But let's take, for example, covariate 0. This is somebody that had stable housing, a low SIR score, and stable employment. So those were sort of the most important features. So this is somebody that you would think would be low risk. There should be very high probability that I'm putting you in the low risk class here. And indeed, remember we want to prioritize low risk class. This is somebody that I'm admitting. So this is my threshold score for admission. These are confidence intervals around that threshold score. This is the dot is at the estimated score, and then I put a confidence interval around the estimated score. And there's, you know, nobody's over 1, so that's why these confidence intervals are not exactly symmetric. Okay, I also have 2 guys here, covariates 1 and 4. You can think of them as the opposites. So unstable housing, high LSAR score, unstable employment. They have a very low priority score, and I don't want to admit them. And the color coding here is green is I've made a correct decision. So the dot and the line is my estimated score and the confidence interval for my estimated score. I've colored it in green because that gives me a correct decision. And the decision is made exactly on the ordering of these dots. Okay? So the way you've seen it, I would rank this covariate above this covariate above this covariate in terms of admission. Here we go to another covariate. This has a pretty wide confidence interval. I don't know what to do with it, but according to the score, I am going to admit it. That turns out, I can compare because I know the ground truth, I can compare, that turns out to be an incorrect decision. So it's misplaced, and it's partially misplaced because really this was my boundary covariate, and I wanted to admit some of it, not admit some of it, but I'm admitting all of it. I have hope of correcting this because admitted covariates I will collect samples from. This is somebody that has a pretty wide confidence interval. I'm denying them, but I won't collect samples from them. And we could do that for everything. What I want you to observe is I have a lot actually of covariates that have pretty wide confidence intervals. And I have a little note, there's more correct decisions when capacity is small or large. So in a way, this capacity being kind of in the middle is the hardest case. You can imagine if I have a lot of capacity, like say my threshold line was here, then I'd be pretty good. Great, I know these are the 2 that I should deny, and that's great. So it's usually the hardest when the capacity is kind of the middle range. Let's think a little bit about the common interventions and what happens. So let's talk about the data gathering. So I can gather data from admitted individuals, and I would update the policy, let's say after each year. So I have my policy, I admit people. If I admit you, I get to gather data on you. I update it after the year. And so that's what I'm plotting. And so this is kind of weird. So here's year 0. I admit some people, I gather data, I change my policy, I adjust my policy, and the cost gets larger. I usually expect that I gather data, it's good, right? This is gather data is bad. And so let's just think about what's happening. Remember, I've got this bias in my data collection. So year 1, I'm admitting covariate N, I'm denying covariate M. I gather more data and I decide that I'm going to admit covariate M because covariate M is not working. I'd estimated the score, too high. But actually, you notice that the M interval is pretty wide. So actually, when I collect more data on covariate M, this confidence interval for M is going to shrink, and the ordering of these 2 dots is going to go back to where it was originally, right? Because I could shrink the confidence interval. I'll gather more data on M. I shrink the confidence interval. The ordering goes back to where it was originally. I will eventually correct that, but it could take me a long time. Okay? So I want to point out that there's non-monotonicity when you're gathering data because you're only living on one sample path. Okay? So sometimes you'll get a sample path that's good, that will be a monotonic decrease, but not always. If I got to do it over the average, on average, you decrease monotonically. But I don't get the average. ARI is living on one sample path. Human in the loop suffers a little bit from the same problem. So human in the loop, this is my rate of human judgment. In the application, I have about 120 people coming in each year that I have to decide whether or not to admit. And this is the rate at which human judgment happens. I'm going to pretend that human judgment is perfect. That would be the gold standard. That's not correct. But if I can't get a good result when human judgment is perfect, then okay. And when human judgment is perfect, if I get to look over every case, I'll do exactly the right thing. But you notice it suffers from the same problem, basically the same problem here. If I just use a little bit of human judgment, I might switch two covariates that I actually shouldn't have switched. I will eventually correct it, but we're pointing out that when I say use human judgment, you kind of want to make sure you use sufficient human judgment. Okay? So it's sort of the same problem here. And same thing, you could get a good sample path. On average, you would do well. So both interventions reduce the cost gap on average, but each realization does not follow monotonicity. So summary. Under strong conditions, so this is likelihood ratio ordering, the priority score policy works well when facing prediction errors. In general, noisy ML predictions result in noisy decision boundary. Still, for some covariates, accurate decision is possible with high confidence. Data gathering or human in the loop interventions should be implemented with caution. Looking ahead, policy implementation, we talked about this. I think this is Frederick's question. Long-term benefit, budgets to adjust cost parameters. Learning with restricted exploration, I think this is a nice problem to think about a little bit more. Fairness, I haven't said anything about fairness, but one of the things we're also thinking about now is this could lead to a policy where you let in everybody with red eyes, but nobody with green eyes. So how do you want to think about that? Do you want to think about that? And so thank you, and any questions?
So I mean, it's not a maths question, but related to the final point about fairness, is it legal to use things like race and